Hello everyone, welcome to Dakshana e-classroom program. So in last lecture we discussed about the measurement of radioactivity. So radioactivity, we saw that it is actually measured in terms of a quantity we define as activity, and activity means it is the rate at which an radioactive nuclei is decaying, it's breaking down, is converting to another nuclei that may be active or radioactive or maybe stable also, right? So we saw about a few more terms, that is half-life. You must understand what is the meaning of half-life, measurement, activity, unit of activity, that is becquerel. SI unit is becquerel, or we call disintegration per second, but radioactivity or activity is also measured in another unit, that is dpm, dph, disintegration per hour, per minute, per day, and we have few more quantities, that is 1 Curie and 1 Rutherford. Is it? You should remember those things. Let's see some application of those. We saw just one application in the last lecture. Let's see with one more, like few more application, then we will move on to the next part in this measurement of activity and solving problem and different types of. So this is also equally important part, because now problems will be asked on the models on the topic which we are going to discuss. So you should understand that how we deal with such problem, how we solve, what is the exactly approach. So pay attention, you will find it easy. Okay, so let's continue here with another example. Let me read the problem first. The number of uranium 238 atom in a ancient rock is equal to number of lead 20. So this number is equal to number of lead Pb 207. Is it? Number of uranium, this is equal to that. Half-life of uranium 238 is this. So T half is also given, that is 4.5 into 10 raised to power 9 years. Remember that. Estimate the age of rock, assuming that all the lead 207 above like atoms are formed from the decay of uranium 238 only. So it's simple problem, but you should understand कि क्या दे रखा है, what is exactly given and what we need to like approach. It's not more about the age, it's just like simple application of activity and number of nuclei. So now see here what is happening actually here. Uranium 238 after decaying so many alpha, beta, and finally it's getting converted into lead 207, 82, and it's 92. So this is the conversion process. So initially, if I say, let's say at T is equal to 0, this is the number of nuclei present, and here this is 0, because it's saying, assuming that all the lead atoms are formed from the decay of this. So initially at the time of formation of rock, we can assume that only uranium 238 was present, and this was having like almost 0 atoms. Now in the current time, is it? So let's say current time, this has been how many? N0 by 2, and this is also N0 by 2, because number of the nuclei decayed will be exactly number of nuclei of this form. Now you understand what is this actually. In what time it decay, or like a number of nuclei or number of radioactive nuclei become half, and that we know it's directly, it is in the duration of half-life. Is it? So number of radioactive nuclei reduces to half in exactly one half-life. So what it means how much is the duration the decay has taken place, for how long, and that is basically simply half-life, because in that time only number of radioactive nuclei will be half. So I can write this duration, or you can write age of the rock, you can write equal to simply T half, and T half, and that is equal to 4.5 into 10 raised to power 9 year old. So the rock is this much year old. So that's a simple straightforward problem, right? I hope like there should not be any confusion. It's basic simple thing, like you should understand the problem, what is given exactly, and how we should like proceed here. That should be clear to you. Okay, another problem here we have half-life of radioactive nuclei is given here. So for some nuclei, radioactive nuclei, half-life is 20 hours, right? What fraction of original activities, let the original activity is A naught. Here you should remember the formulas that we discussed in the last lecture, because it's based on exactly that. So you should know them, you should remember the formulas. Then it's a straightforward, easy problem. Alright, so now it is asking what fraction of original activity will remain after 40 hours. So after 40 hour means what? 20 hour plus 20 hour means you can write 2 times of T half. So how long duration it is we are talking about? That is 2 T half. And in the last lecture we saw that activity is equal to activity divided by 2 raised to power n activity after n half-life. And how many half-lives are there? Here it's 2. So activity I can write after activity of sample remain after 40 hours, that you can write A is equal to what? A naught divided by 2 raised to power 2, that is A naught by 4. So 1/4 of the activity will remain. It's asking about the fraction of original activity. You can calculate fraction is equal to A divided by A naught, and that is 1/4. So we can write here 1/4 of the activity of radioactive nuclei will remain after 40 hour of duration. So this is about simple application of like the part we discussed and simple problems. Try more problems, you will get more confidence on these like topic and part. Okay, let's see one more problem. So the decay constant of radioactive nuclide 64 copper is this. So here you are given with lambda, that is 1.516 into 10 to the minus 5 second inverse. Lambda for copper 64 is given. Find the activity of sample, and here we are asked to find activity, that is dN by dt. This is the objective, we need to find this. Atomic weight of copper is given 63. So atomic weight of copper, this is 63.5 gram per mole. Neglect the mass difference between the given radioisotope and normal copper. So actually here this is the mass of normal copper atom, or we call it basically average mass, because copper has many isotopes, so that's why it's the like average mass of that. So but it's asking, like it's saying for copper 64 also you take the mass, molar mass is equal to same, right? So now the objective is here we need to find this, and we know the formula, it's equal to lambda times n. Lambda we are directly given, so now here we need n. And what is the n? N means number of radioactive nuclide of copper present in 1 gram, is it? So we need to find first here n, that is number of radioactive nuclei of copper 64 present in 1 microgram of 1 microgram mass, right? So we can calculate this n. So n is equal to what? N is equal to, we can write this is equal to, we have already mass, so this is right, so it's 1 into 10 to the power minus 6 divided by what? How many number of mole? It's 63.5 same gram multiplied by Avogadro number 6.022 into 10 to the power 23. You can simplify it, it comes like almost cancel out, so it comes out exactly around 9.45 into 10 to the power. Here it will be what? 23, so it will be like 17, and to this, so it will be like 15 atoms. So we got the number of radioactive nuclei present in this much amount of sample copper 64, is it, or sample, right? Now activity, so activity, simply we can write this, activity is equal to what, lambda times n, that comes out to 1.516 into 10 to the power minus 5 multiplied by 45 into 10 to the power 11, multiplying sorry, it's not 11, it's 15. Okay, and after solving this we get exactly, it's around 9 10. You need to solve it properly, do the calculation part. You can use the calci, but try to avoid, because in IIT calci is not allowed. So try to do the calculation properly. I'm directly writing the result. So it comes after multiplying this, it's like 1.45 into 10 to the power it's 11 dps. So this is the activity actually coming after multiplying and solving this. Sorry, it's actually 1.43, right? Okay, it's like huge value actually, so we can convert the unit also. So this is also equal to 1.43 into 10 to the power 11 divided by 3.7 into 10 to the power 10, right? Because this is dps in what, 1 curie. So I can write this, or 1.43 into 10 to the power 11 BQ Becquerel. It's same thing. Just simplifying this, we get actually around 3.86. Okay, 3.86 Ci. So this is 3.86 curie. This is also right answer. This is also a right answer. This is it, just in different units. So this is how we can simply calculate the activity of any radioactive nuclei. You should have complete information, you should have data provided, do the calculation, apply the relation. Simple, straightforward problems are there. So let's continue here with the next topic, next part, that is average life. Let me explain you what is that. Okay, so the next we are going to talk about is average life. First, you should understand what is actually average life, what it means. Then we will get that formula, just use it. So you must understand its meaning. Okay, let me explain you here with simple example. So let's say we have radioactive nuclei A and decay constant lambda, and it's finally decaying to stable nuclei sum B. So this is the process going on. We know already at T is equal to 0, so it has, let's say, n naught number of nuclei, and it has 0 number of radioactive nuclei at 0 time. After some time T, we get this n, and this will be what, n naught minus n. Means this is the number of radioactive nuclei left for A. So means how many has been decayed, n naught minus n, and exactly that many number of radioactive nuclei B will be formed at by time T, right? So now see, few points I told you yesterday, that even when all n naught number of radioactive nuclei are active, still first thing, it doesn't happen that all the radioactive nuclei are decaying immediately or simultaneously. Some nuclei decay now, some later, and so on. That exactly happened. Which radioactive nuclei will decay when, we can't comment on that. It's just the probability we study here, the probable decay, and we see that more number of the nuclei, more will be the probability of decaying, is it? Or we simply call that higher will be the activity actually. Otherwise lambda remains constant, right? That all those things. So like activity is directly proportional to number of radioactive nuclei present. Okay, so now this is the, now see, n naught was initially present, n is left now at time t. Clear? So what I can say, n naught number of nuclei has survived up to time t, remaining n naught minus n has decayed. They are not now live, they are not surviving now, is it? But I need to calculate. Let me tell you this with simple example. Let's say initially we have 100 radioactive nuclei, and here I will say T half for some imaginary hypothetical radioactive nuclei. Let's say I will say it's, let's say 2 day, right? So I will say after 2 days, how many radioactive nuclei will be there? After 2 days, number of radioactive nuclei left is exactly 50, because it's exactly one half, T half. In one half, radioactive nuclei will be decayed by half. Is it? Half is gone. So if I talk about from 0 to T is equal to 2 days, it's not like that all 50 nuclei has decays exactly after 2 days, right? That is not true. So here after 2 days we can say that exactly half of the nuclei will be decayed. So 50 nuclei has survived up to 2 days, is it? Now if I say 2 days plus some small time dt, and let's say I'm saying in this dt small interval of time, I can say out of these 50 available, let's say dn, and that may be, let's say I will say 5 nuclei decayed in dt time. So what I can say exactly, these dn means 5 nuclei has survived exactly up to what? 2 days dt time. Understanding? 2 plus dt days. Getting it? So exactly now if I multiply this dn with this much duration, then I can write this is the total time for which these nuclei has survived, means total time of all summation. So exactly if I multiply the life and number of nuclei decaying and add it for all number of nuclei, so I can write my total 100 nuclei have survived for which duration, and if I divide that duration by total number of nuclei, then I can write on an average how many or what exactly for what duration each nuclei is surviving, for exactly or for an average what duration each of the nuclei is living. Understanding? This duration, this time is termed as average life. So let me, I hope you are getting you are clear with this point. Let me do the calculation part and let me get the expression for average life. Okay, so we are talking about here this A number of radioactive like A is the radioactive nuclei finally decaying to B, T is equal to 0 and not number of nuclei was present 0. T time N is present, N is left for A, and N naught minus N is formed for B. Is it? Here we are talking about only A, average life of radioactive nuclei, not for B. Is it? Whether it's like if we talk about B, then we will do the calculation for B part. Right now I am talking about average life of A. Okay, so let in time dt dn number of radioactive nuclei of A has decayed, right? So I can say these dn number of nuclei for what duration they have survived. Is it? The life of dn number of nuclei, what I can write, this is equal to total, I'm like their life is what exactly, it's T plus dn. Is it? This you can write T plus dn dt. So total time of survival of dn number of nuclei, what I can write, this is equal to T plus dt multiplied by dn. Right, is it clear? So we can write the total time of survival of dn number of nuclei can be written as T plus dt, is it, and multiplied by dn, right? Just wait one second. Okay, so total time of survival of I can write dn nuclei, we can write this, but here I told you actually this dt is small, is it? So for small value of dt, we can say it's almost tending to 0. So in that case this will be like almost t, and this I can write t into dn, right? Okay, so this is the duration of survival of dn number of nuclei. If I want the total duration of survival of complete total time of survival of n naught number of nuclei, then what I can write, this is equal to integration of t dn total 0 to n naught. I will like for complete I will get this. So this is the total time. Then what is the average life? So what I can write, average life is equal to total time of survival divided by number of radioactive nuclei, will be like, this is the duration for which on an average every nuclei is staying alive, and we call that average life, is it? So you can write here just definition, it is the duration, or I will write average duration, you can write also time, for which each of the radioactive nuclei is surviving. Average of, because if I will say these radioactive nuclei, let's say finally by the time of 100 day all the nuclei are gone, is it? So now n naught multiplied by survival of each nuclei multiplied by time, then I will get total time of survival divided by, let's say, n naught number of nuclei, then I will get around, let's say, 40 days. So means on an average each nuclei is staying alive for 40 days. But here you try to understand it, the thing, it's simple. Actually every nuclei is not surviving for 40 days. It's an average value of the survival. Maybe one nuclei or some nuclei immediately decayed, maybe some nuclei survived even for, let's say, 100 days or even more than that. Understanding? And like maybe some surviving for 90 days, maybe some surviving for 80 days, like that. But on an average I can say that every nuclei is surviving for 40 days. So 40 days is the average life of every radioactive nuclei. So this is, now we can calculate it. So this comes out to be, this is equal to what, integral t dn divided by what, integral dn. So integral dn we already know. And one more thing here, we need to substitute here dn, is it? So for that let me just erase this part. As I know already, for this case I can write n is equal to what, n naught e raised to power minus lambda t. If I differentiate it, then it's dn by dt is equal to lambda n naught minus e raised to power lambda t, and dn is coming out to be e raised to minus lambda t multiplied by dt. So I need to substitute it there, but here this dn I know it will be total number of radioactive nuclei. So this comes out to be integral t, and this is dn minus lambda n naught e raised to power lambda t dt divided by total n naught. N naught cancel here, and lambda simply constant coming out. We should understand this. Okay, let me create space here. Okay, so here now I can solve this further here. This implies, what is left here, lambda outside minus, this is t e raised to power lambda t dt, is it? We can integrate it. So here we need to integrate it by parts, right? Okay, so we can further simplify it, and let me just solve the like erase this part for this space and finish. And also now I'm simplifying it from here. So we got this up to here, and like here n0 simply gets cancelled. Limit of time will be from 0 to infinity till the final decay. So it's a minus. Now we can take it, this is first function, this is second function, this is by integration by part. You must be knowing that method. So that is equal to minus lambda. I'm keeping it outside. So this is first function as it is. Integration of second function, so integration of e raised to power minus lambda t. I hope you can understand if I am going straight forward here directly. Otherwise I can go even step by step also. Dt minus integration differentiation of first function means d by dt of first function t multiplied by integration of second function dt, this complete integration of that. Is it so? This is minus lambda, this is t e raised to a minus lambda t divided by minus lambda minus integration, this is 1 into integration of this e raised to a minus lambda t divided by minus lambda. I am taking it outside directly, I am writing it this into this dt that. Okay, so we got it up to here. Then solving it further, minus lambda, I can take lambda out from there, so it's lambda, it's minus t e raised to a minus lambda t, and solving it further, so it will be like e raised to a minus lambda t divided by minus lambda that I am taking directly. So this is now limit 0 to infinity. Now I can erase this part also. So अभी देखो वैसे मेरे को इसकी ज़रूरत थी थोड़ा सा. Okay, so this is gone, minus we are left with, and this, let me substitute here the limits. So I am taking it out, so it's minus t e raised to power. Now see, if once I will substitute the limit infinity, another I will substitute 0. So when I am substituting here infinity, then it will be 1 by e power infinity, that will be 0. Overall multiplying this, we get actually here 0 minus e raised to power minus lambda into infinity divided by lambda minus, here if I am substituting 0, then again it's 0 minus here e raised to power 0 divided by lambda. This is left. So this is also again becoming infinity, so 1 by infinity e power infinity something, and that will be 0. This complete is 0, and we are left minus 0 minus this minus minus plus, this will be 1, so 1 by lambda. Actually it will be plus, but finally we are getting here minus 1 by lambda, but this is not right. Actually we should not get here minus. Okay, so let me tell you that why we like we should get positive. The point is here, n is this, we write dn by dt, and we used here minus sign only just to show that this rate is decreasing. Clear? But if I am talking about simply dn, then dn is what? Simple number of nuclei. And number of nuclei decayed in any time, that number should be positive. So actually for solving this part, we should not use this minus sign, because here this rate doesn't make sense. Like negative positive is not like used here. Actually we are simply counting the number of radioactive nuclei which is decaying in dt time, and that number, because see this quantity will be positive, so that number cannot be negative. So that's why we should use here negative sign should be removed. So if we make it positive, automatically here it will be positive, this will be positive, this will be this and this, and finally we will get this. So here you can write average life, finally we are getting it's 1 by lambda, or 1 by decay constant. You should remember this formula, it's very easy, straightforward, there should not be any confusion. It's more important is understanding the point that what is exactly the meaning of average life. So I hope you are clear with that part. So this is all about basically the concept, the points that is average life. Let's see some of the application of it, then we will continue with more topics. Okay, so let's see another application of the concept that we just studied. Let me read the problem. Half-life of AU-188. So here you are given T half-life is 2.7 days for AU-198. Now you are asked to calculate the decay constant, means lambda. We need to find time, average life. We need to find activity of, so means activity also of 1 milligram of AU-198, and take the atomic weight of AU-198 to be 198 gram per mole. So this is the problem. I hope you must be understanding it. It's a simple, straightforward problem. Let me simplify it. So we know, let's say, first part, that is a decay constant. So decay constant is what? We know already, like the relation T half, this is what we need to find, equal to 0.693 divided by lambda. We need to find here lambda, so lambda I can write this is equal to 0.693 divided by T half, that is 0.693 divided by 2.7 days, and I can convert it into seconds, then it will be like 693 2.7 days means multiplied by 24 hour multiplied by 3600 seconds. Is it? We can simplify it, and I am writing here again the result directly. You can simplify it. The lambda is coming out to 2.9 into 10 is to power. I am writing the result. It's let me just check it. So it's a 10 to the power minus 6%. This is lambda. Clear? Next is that is average life, B part. Average life, you know, actually it's 1 by lambda. So you can write 1 by, it's 2.9 into 10 to the power minus 6. So this will come out after solving. 1 by 2.9 into 10 to the power 6. Let me just, it's around 3. So it will be in days. This average life will be in second, and I can convert it to day, and this finally solving. So again, this is equal to divided by 3600. Is it? Multiplied by 24 into 1 by 2.9 multiplied by 10 to the power 6, then we are getting average life 3.9 days. Just calculation is there, you need to do it properly. and directly writing the result here and not going for the exact multiplication. You need to do that properly. Okay, but there is nothing conceptually, it's very simple, straightforward problem is there. Okay, let's me just get for the C part, that is activity of 1 milligram. So we know actually activity is equal to what? Decay rate, and that is equal to lambda times n. Clear? So activity lambda times n. So I know already lambda 2.9 into 10 to the power minus 6 per second. N number of radioactive nuclei I need to find. So n is equal to what? Number of radioactive nuclei. This is equal to in how much? 1 milligram of this AU. In 1 milligram of AU-198. This I can write 6.022. I am directly taking it 6 into 23 into 1 divided by 198 into 10 to the power 3 minus 3. Right? After solving this, again you need to do the calculation part. You are getting here actually it's 3.03 into 10 to the power 18 atoms or nuclei. So I got the value of n. Now activity is lambda times n. Lambda is 2.9 into 10 to the power multiplied by this, that is 3.03 into 10 to the power 18. So it will be something like 3 multiplied by 30, which will be like around 8 point something, is it? 2.9. So it comes 8.8 into 10 to the power how much? Solving it comes out 10 to the power 3, yes, 10 to the power 12. Right, so 10 to the power 12 dps. This is the activity. We can convert, we can write this activity in another unit, that is QE. So that is equal to 8.8 into 10 to the power 12 divided by 3.7 into 10 to the power 10, and solving this we get around 240 QE. So this is a simple, straightforward problem. Only calculation part, yes, you need to do it properly. Remaining conceptually, logically, things are very straightforward, very easy. So I hope you're understanding the things. Let's continue. Let's solve the next part, next topic. Okay, so the next topic we are going to talk about is parallel decay. What is meaning of that? Let me tell you first. So up to this time, first thing is we are talking about the measurement of activity. In measurement, we saw like how, at what rate, number of nuclei, if initially and not is the number of nuclei at any time, what will be the number of active nuclei left, how many will be decayed. Then we discussed about more terms, that is average life and half-life, okay, by this time. And we did all these things only for the case when A radioactive nuclei is decaying to B radioactive nuclei. But it's not always that only A is decaying to B, means one radioactive nuclei is decaying to only another radioactive nuclei. Sometime what happen, single radioactive nuclei may be decaying and forming two nuclei, is it? So A may be decaying to B and C. This is called, if the decay is simultaneous, we call this is parallel decay. So sometimes problems are asked, and that too, like, it's good interesting topic. Here good problems are formed actually on this topic. So here what is happening, let me first tell you exactly. Parallel decay. Parallel decay means here A is the radioactive nuclei. I am not taking any specific example, I am taking here general things, is it? And it's, let's say, forming radioactive nuclei B and C, and here it's simultaneously breaking and forming these, is it? So let's say this is A converting to B also, A converting to C also. For A to B, the decay constant is lambda 1. For A to C, the decay constant is lambda 2. In such case, you are again asked to find the number of nuclei of A, like decayed at any time or left at any time, number of nuclei of B formed, number of nuclei of C formed. So such type of problems are asked. So we need to understand that how we can do it. So I will say here I am having here A and B and C, is it? So let at T equal to 0, I am having only radioactive nuclei of A, there is no B, no C. So number of radioactive number of nuclei of B and C are 0, 0. Only A was present at this 0 time, right? Remember that A is decaying to B also, A is decaying to C also. If I know the decay constant of A, is it? Because it's going parallelly two processes, but if I know the average or cumulative or effective decay constant, then by the part that we have studied, I can directly write number of radioactive nuclei of A left, that is equal to simply N is equal to N naught e raised to power lambda effective multiplied by T, is it? So if the effective decay constant for A is lambda effective, or we write it also lambda average, then for A I can write N is equal to N naught e raised to power minus lambda effective multiplied by T. So here I need to get lambda effective or lambda average. for this parallel decay process. We call it parallel decay because it's simultaneously decaying into B and also at the same time like it's decaying to C also. Okay, let at time t, here number of nuclei is n and here it's formed is nb and number of nuclei formed is C, or let me write here left, it's like number of radioactive nuclei of A, left is Na. This is the situation. Now I can write the activity of A, this is equal to what? dNA by dt. This will be what? Lambda effective multiplied by Na, right, at this rate. And A decaying to B, the decay rate of A to B, this can be written as dNA by dt is directly proportional to, I can write proportional to Na, but if I write for B, then I can write this is equal to lambda 1 into Na, right. Similarly dNA, or in, it's not exactly proper, I should not write it actually, but this I think I can write easily, the rate of formation of nuclei B, this I can write that is equal to dNB by dt, this is equal to what? This I can write lambda 1 into NB. Just 1 second, this is actually not rate of formation of okay, just 1 second. Okay, so here actually now we need to write the things properly for B and C, so let me try it a different way. Say, let's say let in time tt dNA number of nuclei of A has decayed, right, and it has been decayed into what? B and C, so I can say let and in same time dNB and dNC number of nuclei of A, B and C are formed. Because A is decaying, then I can write simply dNA should be equal to dNB plus dNC. Is it? One relation. I can, if I divide by dt then I can get the relation in activity dNB by dt plus dNC by dt. So overall this is decaying, the rate at which A is decaying is equal to the rate at which B is formed plus C is formed, is it? And I can write this is proportional to what? Okay, so alright, so I will write here dNA by dt is proportional to what? Na total. Clear? Out of this, right, so I can write this will be also proportional to this, and this is also because if total number of nuclei of A is higher, definitely formation rate for B will be higher, for C also it will be higher, is it? So this will be right proportional to, so I can, this implies dNB by dt will be also proportional to Na and d and c by dt also proportional to Na. Right now, here I can write simply like this is equal to lambda into lambda 1 into Na or lambda 2 into that. We write it simply effective Na. But rate of formation, you can write actually this part, the rate at which this is breaking, is it's forming B and C. So the breaking rate, and from this the breaking rate for the formation of B is equal to the formation of rate of B, and I can write that will be like proportional to what? Lambda 1. So means I can write here actually, okay, so I am erasing this part. This implies d and b by dt is here directly proportional to Na, but here like proportionality will be equal to, you can write lambda 1 into Na, and this implies d and b is equal to lambda 1 and a into dt. Similarly, d and c by dt is equal to what? I can write this is proportional to Na. This implies d and c by dt is equal to, proportionality constant here will be for c, it will be lambda 2 into Na, and here we get d and c is equal to lambda 2 Na into dt. Now see, if I substitute these things here, then what I am getting actually, so we are getting d and a is equal to lambda 1 dB, like d and b, so this is lambda 1 and a dt plus lambda 2 and a dt. Na I can simply, this is equal to lambda effective into Na into dt. Now just comparing and like cancelling out Na and a, we are dt, we are getting lambda effective or lambda average is coming out to simply lambda 1 plus lambda 2. One thing we got this one, right? Now I have this lambda effective, then I can write this is equal to what? Lambda 1 plus lambda 2 into and a. Now if I simplify this, then I can directly write here that Na is equal to n naught e raised to power minus lambda effective lambda 1 lambda 2 into t. So this is the rate of like number of nuclei of A at any time, is it? We have this relation. So by using this relation, let me get the number of nuclei of B at any time and C also, is it? So number of nuclei of B formed, this can be written as d and b by dt is equal to lambda 1 into Na, and Na is equal to this is n naught e raised to power minus lambda 1 lambda 2 into t. Dt can be multiplied there into dt. Now I can integrate it. So 0 to t and 0, it's 0 and nb t time by. So integrating this is nb, lambda 1 constant, n naught constant, integration of e raised to power this is equal to what? E raised to power minus lambda 1 plus lambda 2 into t, this whole divided by minus of lambda 1 plus lambda 2, and this implies lambda 1 by lambda 1 plus lambda 2 into n naught. And now here if I am substituting the limit 0 to t, minus will be also there, minus, if I am substituting t, then I will be getting here, okay, let me write it here only. So we are getting nb is equal to lambda 1 n naught divided by lambda 1 plus lambda 2, and remember this minus will be here, minus. Now I am substituting the limit t, then it will be like e raised to power minus lambda 1 plus lambda 2 into t minus substituting this limit, so it's e power 0 that is equal to 1. Considering this minus, then I'm finally getting nb is equal to lambda 1 and naught divided by lambda 1 plus lambda 2 into 1 minus e raised to power minus lambda 1 lambda 2 into t. So this is the number of nuclei of B formed at any time. Exactly going in same manner, similarly, number of nuclei of C at time t. So and C can be written as lambda 2 n naught lambda 1 lambda 2 1 minus e raised to power lambda 1 plus lambda 2 into t. If you just solve it exactly same manner, then you will get this. So this is the activity of A, like B and C also you can get actually, like the rate of formation of A. So that will be like, simply you can differentiate this and like differentiate this part, then you will get dn b by dt, rate of formation of B, and so on for C. So I hope you are getting this is basically parallel decay process. A is simultaneously decaying into B and C. Here remember that it's not like maybe you are confused that A, let's say A, I will say 256 to 238, it's not like it's breaking and forming 2, like, is it? So just like A, just for example, I'm taking, let's say A, this is 250, let's say, okay, and it's not breaking like B plus C and simultaneously. So this is, let's say, 150 and 100. It's not this decay actually, is it? This is not parallel decay. Understanding? Here it's like some part of A converting into B and some part getting converted into C. So that is this case actually, remember that. So in this situation, we can get the number of nuclei of A at any time, number of nuclei of B, C, activity, rate of formation of B and rate of formation of C, anything can be calculated. You should remember the process, and that's all about parallel decay. Similarly, there is one more decay actually. I told you that earlier, that let's say uranium-238 is decaying, then it's finally after so many decay is getting converted into lead. It's like a next step or next product is not many times A stable nuclei. So A decay to some B, B itself is many times a radioactive nuclei. Then B decay to C, and C maybe finally your stable nuclei. So when this is the process, A decaying to B, B decaying to C, this we call successive disintegration. So exactly in same manner, like sometime you will be asked at what rate B is formed, at what rate C is formed, at what will be the number of nuclei of A, B, C at any time. So similarly, how we can solve, how we can approach that, let's see that next part. Then we will see problem based on it. Okay, so next is successive decay or successive disintegration. So here, let's say A is one of your radioactive nuclei and it's decaying to another radioactive nuclei B. The process or decay constant for this A to B decay is lambda 1. Here B itself is not a stable nuclei. So this is also further decaying with decay constant lambda 2 and forming, let's say, C. Is it? So this is the process, and this decay we call successive decay. So let at t is equal to 0, number of A is, let's say, n naught, number of radioactive nuclei of B is 0, and number of radioactive nuclei of C is also 0. At time, let's say t, I will write A left is Na, B formed is NB, and C formed is NC. Right? Now see, if I just forget about C part, then it's A to B decay is normal process, simple as it is. So here I can write for decay of A to B, this I can write dNA by dt is equal to what? Simple lambda 1 into Na. this rate will be proportional to Na. Proportionality constant will be like lambda 1 here. I can simplify it as it is because n naught simple, so this will get Na is coming out to be n raised to power e1, like n naught into e raised to power lambda 1 into t. Because for decay from A to B, there is nothing, there is no difference, it's simple as decay. Here another thing is that the rate at which A is decaying will be equal to the rate at which B is forming, is it? So the rate of decay of A is equal to rate of formation of B. Clear? So I can write magnitude wise, this is dNA by dt, decay of A equal to dNB by dt, formation of B. But the point is, when B is forming, B itself is not stable nuclei here. B is also a radioactive nuclei. Initially there is no B nuclei, so initially the rate of formation, rate of decay of B will be 0. But after some time, once like few nuclei of B has formed, they will also simultaneously start decaying. And I can write the decay rate, is it? So the decay rate of B, you can write, will be equal to rate of formation of C. So I can write this dNB by dt. This is not effective, it's only decay. Rate of B will be equal to what? dNC by dt. Formation rate of C. Understanding? So now this is simply can be written as lambda 1 into Na. At any time t, if Nb is the number of nuclei of B, then I can write this decay rate, is it? I will write at any time t. I can write dNA by dt is equal to dNB by dt. This is formation equal to lambda 1 into Na, and dNB by dt means decay only. This is only dNB by dt for decay rate. This is directly proportional to, I can write lambda 2 into Nb. Is it clear? Right? So now I can write the effective rate, is it, of the effective rate of change of radioactive nuclei B. This I can write dNB by dt is equal to lambda 1 and A is the rate at which it is forming, and lambda 2 and B is the rate at which it is decaying. So I can write this is the effective rate of change of NB nuclei. I hope you are getting it. Simple thing. A decaying to B. B itself is not stable nuclei. So initially B has 0 number of nuclei. There is no formation of C initially. After some time, when let's say NB is the number of nuclei of B has formed, is it just like some time? Actually here this B NB I am writing is the number of nuclei of net number of nuclei of B at time t. Is it? So by that time some like more number of nuclei has formed, some might have decayed to C. Is it? So this is the number of nuclei of B NB at time t, number of nuclei of C is NC at time t. But I am saying by some time it might have, let's say, I will say at let's say some t time, from here 100 nuclei might have decayed. So here how many, like 100 nuclei might have total formed, but by in same time out of those available 100 some might have decayed. So maybe let's say at time t 100 decayed, 80 this and 20 these formed, so that total is equal to this. I hope you are getting. A decaying to B, B decaying to C. So here, like you might have seen a situation, actually let's say we have one tank, right? When we are opening the tap, then it started filling, but there is small hole at the bottom of the tank. What happened after some time? The water start flowing out from the tank. So effectively there is net change. Let's say first is filling rate is, let's say the rate at which tap is supplying water. Coming out is emptying rate is the rate at which it's coming out. The effective rate in which with which the volume of this tank will rise will be the rate at which it is being filled minus the rate at which it is being emptied. So two processes are happening exactly same time here, and same thing is happening for B. So for B, it is forming at this rate. I'm like at this rate, is it? It is also simultaneously decaying and forming C. So effective rate I can write at any time. This is right that we normal relation we can get it just from here. We can write the effective rate of formation, rate of change of nuclei of B is equal to this. This is formation minus decaying rate. Okay, so we got finally relation here. Here this and B. Now my objective here is to get the number of nuclei of B and number of nuclei of C at any time. Similarly, activity of B and activity of A. So if anything is asked to us about this or related to this, we should be able to answer that. So I am trying to explain that, and by this time I just explained this relation. So I hope you are clear with this relation. Let me just simplify. Let me get up to the final point that we want here. Okay, so now next is we need to simplify this relation, is it? And how to simplify this relation, you should be, I think, familiar with that. So here what I will do, I will write NB by dt plus lambda 2 NB. I am bringing both terms this side, and this is equal to lambda 1 into NA. To integrate this type, actually we should have information, we should have idea how to solve this type of integration here. NB, NB and NA, or like three things are there, but this can be actually rearranged to some form by application of, by using integrating or integration factor. Now you need to decide what should be your integration factor here actually, right? So here integrating factor will be e raised to power here lambda 2 into t. Right? So now see, if I multiply it here, understanding, then what I will get here, it's coming out to be e raised to power lambda 2 into t dnb by dt plus lambda 2 e raised to power lambda 2 into nb into t into nb. This is equal to lambda 1 e raised to power lambda 1 t, just one second, lambda 2 t into Na. So I am trying to solve. Let me just erase this part. Try to pay attention. Integration, if you are knowing it, then it should not be a problem for you. If you don't know the integration of this part, then you might be like, you need to focus more here actually. So here the point is, here we solve this type of integration by using an integration factor. Integrating factor, how to choose, you should be familiar, you should study that in your mathematics 12th part, that is integration part. Okay, so this is up to here. Now I can rearrange it this little bit also. This can be written as d by dt of basically, is it this? So these two parts actually cumulatively I can write d by dt of c. Listen, this is e raised to power lambda 2 into t into nb. Because now see, if you differentiate this, then what will be like here, you will be differentiating once, it's like product of two function. So you will be differentiating this, is it? So if I differentiate this, then what I will be getting this nb into e raised to power lambda 2 into t into lambda 2 plus, next time I am keeping this constants, e raised to power lambda 2 into t into differentiation and b by dt. So means this quantity is equal to this, means this quantity complete, right? You must be getting it, is actually this. So I can write this quantity is equivalent to this on left side. right? Point is, this is the method of integrating factor. We multiplied the complete relation with integrating factor, that is e raised to power lambda 2 into t. We should have like idea this, you should get it from like a method how to solve in your mathematics, you must have studied that. So we got this. Now see this quantity. Okay, so now from here we got actually this relation is equivalent to this. Now by using this, I can write this term is equivalent to that, and this implies d by dt of e raised to power lambda 2 into t into nb equal to this lambda 1 e raised to power lambda 2 into t into this na. We already got na is equal to what? And not e raised to power minus lambda 1 into t, right? And now I can multiply this term dt there, then I am left with, let me solve it next step. So d of e raised to power lambda 2 t into nb equal to lambda 1, if I just rearrange this, and not e raised to power lambda 2 minus lambda 1 into t into dt. Next I can integrate it both side. So integration of d of something, is it, and this integration, so here it will be like integrating this is equal to simply e raised to power lambda 2 into dt into nb. Clear? On this side I am getting actually lambda 1 and not simply common, and this is 0 to t. Is it? I need to substitute the limits here also. So here if I substitute the limit, then at 0 to t, right, nb is 0, at t time it will be nb, so on this side it will be 0 to, here you can write directly, at nb initially it's 0 and at time t it's this, so I will get on this side it's this one exactly. Integrating this, I will get e raised to power lambda 2 minus lambda 1 into t divided by what? It's lambda 2 minus lambda 1. Is it? So just one sec, let me check the calculation part here. So we are up to here, we got this, that's correct, no doubt. And then na we have already written, na is equal to what? N naught e raised to power minus lambda 1 into t. So we substituted the value for n and here plus signs, that integration factor is also right. Okay, just we need to simplify it now. So now after solving this, we can get this implies nb, this is lambda 1. Okay, before that we need to substitute here limits also, 0 to t, right? Just wait, let me check the calculation. Okay, so next is, after simply simplifying this, I am substituting the limits. So here I am getting e raised to power lambda 2 into nb, and here lambda 1 and not simply divided by lambda 2 minus lambda 1 is out. On this side, if I am substituting the limit t, then it's e raised to power lambda 2 minus lambda 1 into t minus substituting the limits 0 e power 0, that will be equal to 1. Let me divide it by this side and rearrange it. So finally I am getting nb is equal to lambda 1 divided by lambda 2 minus lambda 1 into n naught, and this is coming out to minus lambda 1 into t minus e raised to power lambda 2 into t. So this is the number of nuclei of B formed at any time t. Effectively it's coming out to be this. You should remember this result actually, because it's used like many times in some problem it is asked. So you will have two options, either go exactly step by step and derive it, another way is to remember it. And remembering, I think it's not that much difficult. NB is, you can easily just, if you write it 4-5 times or 10 times something, you will be like able to remember it and use it sometime like in problems, then it will be clear to you actually. So this here we got the number of like nuclei of B formed at any time t. Similarly, we can also get the formation rate or the rate of formation or even formation of B or also number of nuclei of C at any time. So let me simplify for that part. Okay, so now we got NB, is it? So to calculate, to get this NC as function of time, we can go two way. One way is, see, initially total number of nuclei is N naught. At any time t, I can write number of nuclei of A left plus B formed plus C. So if I add all these, that should be equal to initially, because it was only N naught. I know NA, I got NB, then I can get the relation of C, is it? So one way is, I can write N naught is equal to Na plus Nb plus Nc, and this implies Nc is equal to N naught minus Na plus Nb. And Na plus Na I got already, Nb I am having this. Substituting it here, simplifying, you will get the number of nuclei of C at any time. Relation will be a little bit lengthy. Yes, you need to substitute those things and you will get the answer. You will get the expression for NC. Another way is, we already got NB. So we know actually D and C, you can write it, this is second way approach. D and C by dt is equal to what? Lambda 2 into NB. This is the rate of formation of just wait one second. Yes, rate of formation, this will be equal to what? Decay rate, just one, I write D and B by dt. See, this is what? Net number of nuclei of B at any time t. So I can write rate of formation is equal to decay rate or D and B by dt into this decay rate, is it? So I can just calculate d and b by dt, then equating it, then from here also we can get, but it will be little bit even more lengthier. Instead of going for this, you can go easily here onward, because you can see this expression seems to be little bit lengthy, so definitely this calculation part will be also little bit complex. So not go with this way, it's easier to go this way. So NC, N naught you already know, Na also we have, Nb we also have. Simply substitute the values there and we can get the number of nuclei of C also at any time. So this is all about the successive decay or successive disintegration. So we talked about here successive and parallel decay. These are two types of decays. Many times problems are asked based on it. Let's see some application of these two concepts in the next lecture. Thank you so much.